Dr. David Alexander, I'm sure many of you know, is professor of physics and astronomy at Rice University, and he is also the director of the Rice Space Institute, which is an important component of the Rice campus. Maybe David will tell you a little bit more, but the goals of the Rice Space Institute are to help folks learn more about space and also to develop relationships with other organizations that are involved in space, such as NASA. And David has done a wonderful job of that. David has his PhD from Glasgow University in Scotland, the UK. He did his undergraduate degrees and his PhD there. His PhD was in relativistic cosmology, which is pretty sophisticated stuff. More recently, his area of expertise is solar physics, and specifically the solar corona, which is the outer atmosphere of the sun, as I'm sure he will tell you. David came to Rice in 2003 from Lockheed Martin. He has a very strong reputation as a solar physicist. He served on many committees and has chaired many important committees. It's really a pleasure to welcome David tonight, speaking on the topic, the dynamic sun. Thank you.
Thanks, John. So the first test of my ability is if I got the microphone working. We got it? Well, it's a great pleasure to be here. I've actually talked in a couple of John's classes, and it's always been really exciting as a presenter because it's always a very engaging audience. I wish my undergraduates were as engaging and wanted to know as much. I think the last talk I gave, I put a slide like this up, and for the first 40 minutes I was on this slide. There were so many questions. You can do that to me if you want, but I'd rather you waited until maybe the end. And so it's a great pleasure to come back to the program and help it. And before I go on to the actual talk, I have to do a plug a little bit. So most of you may recognize some faces. We have the Houston Spaceport Frontier Lecture Series that we have run for the last several years. And I just wanted to announce our speakers coming up in this year's program. Thursday, September 11, Wayne Hale, who used to run the Space Shuttle program at Johnson Space Center, is a very, what we call in Scotland, a well-kent face, a very well-known person in the field. So we're really excited to have Wayne, and he's a Rice graduate too. Kelly Girardi is the communications director for the Commercial Spaceflight Federation, and she's just a blast. That was meant to be a pun. She not only is working with the Commercial Spaceflight Federation, who represent the interests of commercial space, SpaceX, many different companies, but she's also a candidate for that one-way trip to Mars. So she's a very interesting individual. I met her at a new space conference in San Jose a couple of weeks ago, having already invited her, and so I'm really excited about that. That's going to be October 2nd. Many of you may have heard Houston Matters at lunchtime. Eric Berger was talking. He's been writing a series of articles called Adrift about the current plans of NASA, the Space Launch System, and so on. We haven't set up a date for him yet because he's the most flexible because he's in town. So we'll be setting that date soon. And then we have this talk about exoplanets and life elsewhere in the solar system and elsewhere in the galaxy. A topic that keeps coming up is the moon Europa. And so Robert Pappalardo is one of the key guys at Jet Propulsion Lab on these moons of Jupiter and Saturn. And he's going to be coming and talking about the plans for a mission to Europa to drill through the 10 meters of ice and get into that, what we think is liquid water underneath that substance. We may have some other talks. You can see us at rsi.rice.edu. If you want to get information about the talks that we have, you can go to spacefrontiers.rice.edu. And if you sign up, the only mail we ever send you is about the talks. We're not doing anything else with that. So that's one way of getting that information. So the topic's the dynamic sun. What I'm going to try and do, and those of you who have been in John's class or been in my classes know that I tend to get over-enthusiastic, which means I don't get very far in. I'm going to try and be disciplined and tell you one story of the many stories that you could tell about the sun. I'm going to try and talk to you specifically about the process that drives the sun's dynamism, and that is the magnetic field. There's going to be a little bit of very little sliver of stuff that happens inside the sun, and the rest will be what goes on the outside, and what we're actually bathed in the solar atmosphere and the effects that it has. I do want you to leave you with two things. If you go to sleep for the rest of the talk, two things. The first one is the sun isn't a big burning ball of gas. It doesn't burn anything. You need oxygen to burn stuff. So that's one misconception that a lot of people have. It is an energy-producing machine. And that machine produces energy across the electromagnetic spectrum, radio waves, gamma rays, X-rays, the works, UV. It also produces particle radiation, high-energy particles, protons, electrons, what we call alpha particles, or the nuclei of helium. And it sends those out into space, some of which impact the Earth, the space station, astronauts, you and me. In fact, if you held up your thumb, every second there's about 1 trillion neutrinos passing through your thumb coming from the sun. So there's a lot of stuff going on in the sun, and I've already wasted 2 minutes of my time telling you that and taking away from the one thing I want to tell you. Now, the other thing I want to make clear is if you talk to, I don't know if any of my astrophysics colleagues are in the audience, if you talk to the astrophysicists and astronomers, the sun's really boring. It's a single star, it's not a doublet or a triplet. It sits here in the main sequence. It's a pretty small star compared to some of these guys. It's not very hot compared to these guys. It's not very interesting like black holes and white dwarfs and supergiants and so on. As the Hitchhiker Guide said, it's a mediocre star. Except this quote from a colleague of mine, it's the only star we know of that grows vegetables. And what that means, I'm sure you got, is it's the only star we know of that supports life. So not only is it important for us, because we wouldn't be here to ask these questions if it wasn't for the sun, but it's also important for us to understand how stars interact with planets and whether there's a chance that we might be able to detect life elsewhere, not just within the solar system, but in other we're now, as you're probably aware, and I don't have time to talk about, we are constantly discovering planets around other stars now. The Kepler mission, which had a little problem, but it's now in its phase 2, discovered, I think there's close to 4,000 planetary candidates, 2,000 or so have been confirmed. Some of those are Earth-like, and some of them are in what they call the Goldilocks zone, where the temperature is just right for liquid water, and we believe liquid water, at least, I always get asked the question, does it have to be carbon-based life and does it have to be liquid water? Maybe not, but as far as we know, liquid water is really good. And that's a good thing to have as a first target if you're going to look for a planet that might harbor life. But right now, the sun is it, so far, right? Now, let me ask you a question. I may forget my slides coming up, I'm getting old. But if I was to ask you, if you were to go out when it gets dark later tonight, and we're close to the stadium, but I don't know if the lights will be on. If you were to look up in the sky and see the stars, what does a star look like? What does a star look like? And I've got a microphone, you guys don't, so please shout. You have to shout louder than that. I want everybody to hear you. Pretend you're giving a look. What does it look like?
A white dot.
A white dot. Occasionally, if you peer carefully and it's a nice clear night, you might see a red dot. If you look at Betelgeuse or Aldebaran or so on. If you've gone to a telescope, George Observatory, even the Rice Observatory, and you've looked at the stars, what does it look like? It's a little dot, right? Tell these astrophysicists, how can that be interesting? Yeah, one dot might turn into 2 dots because it's a double star. Might turn into 3 dots because it's 3 stars. Huh? Here's what a star looks like. My editing's not all that good. That's my whole talk, by the way. So I hope you were paying attention. the sun is a star, mediocre or otherwise. It's a star that happens to be very, very close to us. It's 150 million kilometers away. Some of you older people might remember it as 93 million miles. It's 93 million miles away. But our telescopes are so good now that we can actually, if we could turn those telescopes around and change the wavelength and do a couple of other things, and they could actually orbit the sun because it's so kind of hot, you'd be able to separate Hobby Airport from Bush Airport. That's how good we can look at this. That's how well we can look at this star. So one of the things, and I don't have time to go into all of this, one of the things that we can do is we can pick out individual structures in the atmosphere. This is a picture of the atmosphere of the sun. The sun that you would see if you were silly enough to stare at it with your naked eye. Please don't do that. But the sun that you see is the visible surface of the sun. We call it the photosphere. And it emits in the visible spectrum. That's why our eyes are sensitive to red through blue. But the atmosphere of the sun, and this is actually a big problem, the atmosphere of the sun is a lot hotter. The surface of the sun is about 6,000 degrees Fahrenheit, Kelvin, pick your units, right? It's 6,000 degrees. And so hey, Eagle, that's my buddy. As the energy that produces photons, light in the rainbow of colors, the spectrum that we're used to. The atmosphere is at least 1,000,000 degrees Kelvin. 1,000 times or 200 times or so hotter, and can in some cases get up to 20 million. That means that the energy is so high that the photons, the pieces of light, are so energetic that they're in the gamma ray range, the X-ray range, the ultraviolet range. And the good thing for us is that radiation doesn't make it to the ground. If it did, we'd still be a pile of sludge sitting in some backwater in, in Gaia or whatever Earth would have been called. Because all that high energy radiation, if it was to make it to the surface, breaks up complex molecules. You'd never get amino acids forming, you'd never get us. It's bad if you're an astronomer because you can't see it from the ground, so you have to do clever things. And the clever things we do is go into space. So we fly telescopes, not the Hubble Space Telescope. The astronomers refuse point blank to point Hubble at the sun, despite always trying to get them to do it. We'd get really, really good observations for about 3 seconds, and then that would be the end of the mission. But we have built a whole series of other telescopes, and again, that's a whole other lecture, where we've gone into space and we've studied these high energy emissions from the sun. And in part, that's what I'm going to tell you about. That's what I'm going to finish with. What I want to do is tell the story of where that energy comes from a little bit, and that's where the magnetic field, a lot of people don't understand necessarily that the sun and many stars are magnetic stars. They actually are driven in part, a lot of the activity they have are driven in part by the creation of magnetic fields. And you'll see how that shows up. And someone removed my elastic band that was up. Oh no, you will see an elastic band is actually very important. So don't let, if I haven't shown you the elastic band, that means I've forgotten, please remind me, and I'll show you what the elastic band, why it's important. Okay. Way back before the dinosaurs, et cetera, et cetera. The reason, so I'm not going to tell you the whole story of the sun's evolution. There's a lot of stuff that could be gone into. But it's important to understand some of the rudiments that come in. So we think, and this actually goes back to philosophers like Immanuel Kant, who had this idea that the sun formed out of a collapsing cloud of gas and dust. And we know that that has to happen because the universe itself only produced hydrogen and helium and a little bit of lithium, very light elements. We're made of carbon, we've got phosphorus, we've got oxygen, we've got all sorts of heavier elements, a little bit of iron. All of the elements above lithium were produced in the cores of stars. Now the problem is, if all the stars were created at once in the beginning, none of that material would ever make it out. It would never get processed and then make it out. So what we rely on is stars who have been formed very early, went through a rapid evolution. Some of these big stars can last maybe only 1 million years. In contrast, a star like the sun lasts 10 billion years on the main sequence, which is where it turns hydrogen into helium. That's another story. And so those stars that go through this rapid evolution tend to be very large, and because of that, they tend to undergo a supernova explosion. And what that does is it takes all of this material that they've made up and distributed it across the galaxy. Gravity always wins. Gravity always wins in the end, and so gravity over time pulls all that material together into these clouds, and they still contract under gravity. Carl Sagan once said, I don't know if I've forgotten his name. Who's the guy doing Cosmos now? Neil, sorry, how can I forget Neil? I don't know if Neil deGrasse Tyson said it in the current version, but Carl Sagan said, we're all made of star stuff. Yes. Every atom that is in your body, was created in a star. It's been around the block a bit, but it's been made in a star. And this is how it happens. So gravity always wins. So what you have is this big, large cloud. It typically is about a light year across, which is bigger than what I'm showing here. It's a light year across. And it's rotating slowly, and it's collapsing under gravity. And that's important because as it collapses, you have to conserve energy, a fundamental law of physics, and you have to conserve momentum. So what you end up having is a collapsing body that gets denser in the core, lighter further out, and now there's all these interactions between the different chunks of material in this gas and dust cloud. And that's important because what that does, and this is a kind of poor analogy, but if you were all to rub your hands together, we don't do this enough in Houston, but if you lived in Montana, you'd be rubbing your hands a lot, they heat up. So what's happening is as this diffuse gas collapses, when it gets more dense, there are more collisions between the particles. And as there's more collisions, there's sharing of energy and the core heats up. So not only do you get a denser core, and the density falls off with distance, but you also get a temperature structure that falls off with distance. And that becomes important for two stories. One is what the inside of the sun looks like, and then what the solar system looks like. I'm not going to talk about the solar system part, I'm going to talk about the sun. And here's a little movie to sort of give you that kind of representation. You've got this rotation, the skater's arms are out, the skater's arms are coming in as they're spinning, and so it goes faster. You get this hot core, you get this density structure, you get the temperature building up in here. Suddenly the star switches on, it becomes a star. It starts turning hydrogen into helium. That produces energy, wipes out all this junk. What we're left with is little gravitational clumps that ultimately turn into planets. And there's a whole story behind that. And what we don't know yet is whether that's the same process in all. Now that we have more systems to look at, 10 years ago, we had the solar system and that was it. Now we have other systems and we can start to ask some of these questions. But that's another story. And so why is that important? So here's a little bit of physics. Why is that important for a star? So again, what you've done, if you take, if you heat up, so this is mostly hydrogen. Like I said, there's a little bit of carbon, a little bit of iron, a little bit of phosphorus, all these different things. But it's mostly hydrogen. Hydrogen atoms, maybe even H2 molecules, molecules. So the electrons and the protons are together. As you get into these collisional area where you heat everything up, you start to have enough energy to kick the electrons off of the protons. So now you have free protons and free electrons. Now you try and take a proton and stick it to another proton. You ever played with bar magnets, like where you try and push the magnets together, right? So I'm sure the women in the audience tried to push them together and going, oh, they repel each other, that's good, I'm done. And the guys thought, I'm stronger than this, I'm going to make them hit, right? So you can make them hit. They may slide off depending on the strength of the magnet, but you can make them hit because you're using enough force to overcome that weak force of these weak magnets. Well, that's what happens in the core of this collapsing object before it becomes a star, is that these protons are zooming around. As the temperature goes up, one way of thinking about temperature is how fast are the particles moving, right? Ice particles jiggle in place, they don't move very fast. Water particles move quite fast. Gas particles are all over the place. So these particles are moving really, really quickly. And what that means is as they come together, it's like the magnets, they can overcome that repulsive force, the Coulomb force, that means that two similarly charged objects will repel each other. They can overcome those forces. And when that happens, you get a proton interacting with a proton to produce an isotope of hydrogen, it's called. And this is deuterium. So now it's still got only one proton, but now there's a neutron in there. And there's a little bit of, there's a positron released, and there's a neutrino. That's one of those guys that's passing through your thumb. There's the free electrons that came from the original hydrogen atoms, and that interacts with the positron. This is matter and antimatter, so it annihilates to produce energy. Now you've got a deuterium atom flying around. Now these things only last a very short time. We're talking about, I don't know, what, 10 to the minus 15 seconds or something. But the collisions are so rapid that before it gets a time to break up, it gets hit by another proton. And so what happens is, you now slam a proton into this deuterium, and now you've done something really special. You've created a new element. Now the core, this ion, there's still no electrons attached to this thing, it's still too hot, has two protons and one neutron. That's a new element, that's helium. And it's this isotope of helium, it's not the common helium, it's called helium-3 because it's got 1, 2, 3 nuclei. Now you've done this twice, you do this twice, and in fact it turns out we do it 10 to the 26 times, which is a big number. I can't remember how many. It's a big number. And so you have another one of these helium-3 comes in and interacts with that helium-3, and you create a different form of helium called helium-4, which is a bit more stable and more common. And in that process, it releases 2 of the protons, because you've got 6 nuclei, 3 and 3. Helium-4 has 4, and you've got 2 left over, 2 protons. They can then go back into producing more helium. So if you do the math, you put in 2 protons, you put in 3 protons to get a helium-3. You put another 3 protons in to get another helium-3, so you've used 6 protons. I don't have enough fingers, but you get the idea. You get 6 protons, and you get 2 out. So you've used 4 protons to produce 1 helium nuclei. Right, that's the math. What's interesting about that is that a helium nuclei is slightly less massive than 4 protons. So in other words, this, if you added up all the masses, that's slightly less than if you added up all the masses here. There's a little bit of mass goes into the positron, but that's 1,000th or 2,000ths of the proton mass. So where is the extra mass? And the one equation I'm going to give you tonight is E equals mc squared, right? You may not have done physics at school, you may not have done math, you may hate it, as far as I know. I'm sure everybody's heard E equals mc squared. This is how E equals mc squared works, and it works for us. The little bit of mass that's left over gets converted into quite a lot of energy. Now you have a process in which this collapsing gas and dust turns into ultimately a shining object. You have produced a star. And the best star in the whole galaxy and the universe is the sun. Right? Oh, and I asked you that question, but E equals mc squared was up there, so I have to watch that when I do my classes. So what you've done here, again, that's a little bit of physics, and it's not really, and I've taken more time than I really wanted, as usual. But what we've done here is we've said, there's this galaxy out there, it's doing some really cool stuff. Gravity's working, it brings all this stuff together, and then because of very simple physics, it starts to produce extra heat that allows these protons to interact. Nuclear fusion takes over. Because of that process and because it's exothermic, it produces energy. We end up with a machine at the center of this star producing helium from hydrogen and excess energy. And it's that excess energy that then starts to make its way, and this applies to all stars, it makes its way through the rest of that object. The sun is about 700,000 kilometers in radius, so that's about 1,000 times the size of the Earth in diameter. So there's a, did I get that right? 100 times the size of the Earth, I beg your pardon. So there's 1 million Earths can fit inside in the sun. But what's interesting is that energy then starts to get distributed around the rest of this. Remember, it had some of its own energy because it's a little bit less hot. So there's no nuclear fusion going on outside the core, but it still has some energy. But now the core is producing all this energy that then gets distributed. And different stars do different things. I'm going to talk about the sun, in which, because of the physics in there of how the temperature gradients work and because of the density structure, what happens is you have 2 distinct regions. This interior part is called the radiative interior. I'll come back to that in a second, or the radiative zone sometimes. This outer part is called the convection zone. So the sun is a star that has a radiative interior and a convective envelope. Some stars are all convective. I don't know if there's any stars that are all radiative, but it's very hard to get stable convection. Now, the way to think about this is what the radiative interior means is that the energy that's being produced in the core is being transmitted through the star via radiation. So I have a little analogy that might work. So you're at some event, you're at the school your kid's school concert, and you're crammed into the gym, right? And it's so packed, everybody's shoulder to shoulder. The best they can do is maybe move their arm a little bit. The guy in this corner is feeling faint. The faucet's in that corner. Big call goes up, get him a drink of water. Person by the faucet picks up, fills the cup with water. And I should have pointed out, everybody's got an empty cup. So what that person has to do is tip the water into the next cup. That person can only turn in a certain way. Eventually, that water, because there's a direction implied, the guy fainting, that water will make its way across. It may even do a random walk. But that water, that photon, that energy, will make its way through that structure, finally get to the other corner. So that's what the radiation zone is. Each atom is being energized, and so it gets into an excited state. So it gets extra energy. It relaxes and sends off energy that gets transmitted, and it gets radiated in all directions. So it doesn't always have to go out, but the overall trend is outward because of the temperature structure. So that's how, so the cup analogy is to give you that sense is, here comes a bunch of energy, the atom soaks it up, emits it in this direction, another atom soaks it up, emits it, and eventually it makes its way towards the surface. Now, because of the nature of that core and the size of the sun, particularly really it's the mass of the sun that determines all of this, the reaction rate, all of that different thing, once you get to about 2/3 of the way out, 0.7 of the way out, the temperature gradients are relaxing, the temperature's cooling. Radiative energy transfer doesn't work as well. But now you have a new energy process called convection. And you're all familiar with convection. You may even have convection ovens. You heat something in the bottom and it rises. And so as it rises, it shares the energy above, and as it rises, it cools and falls back down. Seagulls use it, geothermals. Jupiter uses it, which is why you get the bands in Jupiter. The sun uses it, the earth uses it. If you're making porridge, you use it, right? And so that's what happens. So now there's a convective envelope. Now, I said I was going to talk about magnetic field. Why am I wasting my time on this? So the key thing is that then is a linked set of linked processes that define the interior structure of the sun. And what's interesting for the sun's perspective is this transition from a radiative interior to a convective envelope. And I haven't even got to the surface yet. Here's the porridge mixer. To show that we know what we're talking about. Now, inside the sun, we now can probe inside the sun. That's another story. But we actually can do seismic studies and actually get a good handle on what the inside of the sun looks like, at least some properties of it. But this is actually an actual movie from, I think, from La Palma telescope looking at the surface of the sun. And you could, if I told you this, if I put a circle around that and said it was porridge, you probably would believe me. Or soup, or stew, or whatever, gumbo, right? Where it's bright is where it's hottest. That's the rising stuff. It rises, moves to the side, and falls down. And when it falls down, it cools, so it becomes dark. Each one of these granules, this is called granulation, each one of these granules is about the size of Texas, give or take. And so that's just evidence that we have these convective patterns happening some distance below the surface and having its manifestation on the surface itself. Why is that important for the magnetic field? Now, this is kind of complicated. I'll show you a movie that hopefully explains it a little bit. What we're looking at here, like I said, we can now probe the inside of the sun. We do it by looking at the sun rings like a bell, so we do it by looking at the surface, and by looking at all of the oscillations on the surface, we can get a handle on what the ray of light that produced the thing that we're looking at, what it did when it was under the surface. A close analogy, I guess, is if there was an earthquake in Tokyo, you would be able to determine how deep it was by the signal. Tokyo wouldn't have a signal, right? But you would be able to detect it in seismic detectors in Russia, in California, in the US, and Europe. And by looking at how long it took those signals to get there, you could actually say something about the material the wave moved through. We can do the same on the sun, except it's not earthquakes, it's the whole sun, and there's a whole bunch of things going on. When we do that, you can actually, one of the properties you can get is how fast different parts of the sun are moving. The whole sun rotates, and it actually rotates like Jupiter in the sense that, so what this is showing is that the pointer doesn't work. Oh, there we go. What this is showing is, so here 1 is the solar surface, 1 solar radii. 0.7 is the transition from the radiative interior to the convective envelope, and we call this the tachocline. And if any of you know any Greek, you'll know that tacho has got something to do with speed, your tachometer in your car. That's because there's a big transition, and that's what I'll talk about. Red is, so this is, because we're measuring oscillations, we talk in terms of frequencies, nanohertz, but if you look on the right, this is the number of days it takes that part of the sun to rotate. So 25.6 days near the equator, 25.7 days near the equator, close to 32, 34 days up near the poles. The sun rotates what we call differentially. The equator goes faster than the poles. And there's a gradation which you can see here. Now we see that on the surface. I haven't got a plot of the surface. We see this on the surface with sunspots. We can watch sunspots move across the sun, and you can see them go faster near the equator. And that's one of the things that Galileo studied with sunspots. What's interesting, though, now that we can probe this, is look at the radiative interior. It's all one color. The radiative interior is rotating like a solid ball. So what you have is a solid ball, rapidly rotating, covered with a convective envelope that's doing two things. It's also rotating, but it's rotating different rates at different pieces of that sphere, and it's convecting. So there's these motions going this way. The sun is rotating this way fast and slow. The interior is going really fast, and then there's these motions of the convection. So what you have, and you all know this, although you probably don't think you do, is you have charges because it's so hot that everything's ionized, so you have protons and electrons. So you have charge, and you have a conducting medium, and the charges are moving. So you all done this experiment in high school, however many years ago it was, where you took a wire and wrapped it around a piece of metal and stuck it up to a meter and passed a current through it and measured magnetic field. Moving charge around a conductor will produce a magnetic field. This is the machine that produces a magnetic field. This plot is just a way of looking at this. This is your differential rotation on the surface, and then this is a single rotation in the radiative interior. So what we have is this large 700,000 kilometer radius, 1.4 million kilometer diameter machine for producing magnetic field. And this is a cartoon that sort of shows how that works, because this is very important. This is the source of energy. This is where the elastic band is going to come in. It's the source of energy for all of the stuff that makes the sun dynamic. One way of picturing this, although it's a bit more complicated, is if you imagine it's just a regular magnet, a north pole and a south pole, and the magnetic field is pointing in that direction. As the sun rotates, the equator is moving faster than higher latitudes, and so you get this bending of the field, and you eventually get lapping. The person in the inner circle is moving faster than the people, and so they lap each other. And what that does is tend to put a slope in the field and intensify the field locally. The field comes together. When it comes together down in here, it acts like it's had extra energy pumped into it, so it acts like a hot air balloon, and it becomes buoyant. And it works its way up to the surface. And then we get the really cool stuff. So let me show you two movies to try and emphasize what I just said in this story. This is really complicated. Don't expect to understand it all, but what it's showing you is that we're modeling. This is a model of all of those processes going on and how this field evolves and ultimately produces sunspots. And then the other movie actually shows something similar in a little bit more graphic form. So let me do full screen. And I think if I did that. So there's your sunspots. This is faster than real time. And then we're just looking at some models. So here's your tachocline region, there's your radiative interior, here's your wrapped around field, it's intensifying, and it's all coming buoyant. And where it starts to stick out here, that's a sunspot. And I'll show you that in a second. This is so this material in here, the magnetic field is being produced low down. It's buoyant, and it comes up, and it pops through the surface. And when it pops through the surface, you have a localized region of strong magnetic field that we see as a sunspot. It's dark because the magnetic field acts like a straw and stops the convection. So you don't get a transfer of energy as much, and so a sunspot is about 1,000 degrees cooler than the rest of the surface. Now, if you could take a sunspot off the sun and hold it up, it would blind you. It's still hot enough to actually be very bright. But in contrast against the much hotter and much larger surroundings, it shows up as dark. And so it's a spot, and it's on the sun, and we're really good at naming things, so we call it a sunspot. Now, again, this is all numerical. Here's another. What you're going to see here, the bottom sliver is the vertical cut underneath the surface, and the top part is a picture of the surface. And again, I'll emphasize it's a model. Here's this flux coming up, the magnetic field coming up. It's very turbulent. Hits the surface, starts to appear, positive and negative, because you're seeing twisted structures showing field pointing outwards and field pointing inwards. And as time develops, instead of being a lot of little things, you start to get large coordinated structures forming. Here's a negative polarity sunspot, and here's a positive polarity sunspot. So you're actually producing sunspots. They are localized regions of strong magnetic field. And I'll show you another movie of how that then relates to the atmosphere above it. And this is really cool. I mean, we couldn't do this 5 years ago. This is the increase in the power of computers and so on. We can start to, and I say we, I couldn't do this in a month of Sundays. But some colleagues, this is from Mark Chung at Lockheed Martin, where I used to work. A lot of really clever stuff going into all of this. So we're starting with the modeling, with the observations that we have, and with basic physical concepts, we're starting to really get an understanding of how a star like the sun works. And that's in part, what keeps us going and why we're interested in it. And then just to show you what a real sunspot looks like, and we actually took this from the ground or from La Palma. Here's this, and the clock, by the way, isn't real yet. There's no clocks on the sun. Right. You see this, here's this granulation. Here's this thing I was showing you. Here's the porridge. If you notice, you can still see some of it. These are magnetic field lines with dark, cool material. This is called the penumbra, and this is of a specific one of the sunspot. And here's the umbra. Umbra means shadow. Penumbra means nearly shadow. So here's nearly shadow, and here's shadow. And the convection, you can't see any convection in here. It's completely subsumed, and that relates to the suppression of the convection. So what we've done now is we've gone from this big cloud, collapsed it to a core. Because of the heat and so on, we've been able to generate energy that then gets distributed through the interior of this object. And then because the energy and the temperatures are hot enough, this stuff is all ionized, it's all charged, and it's moving really quickly in lots of different ways, and so you end up generating magnetic field. That magnetic field says, I don't like it down here, works its way to the surface, and we start to see the kinds of things that we can observe now. We can see sunspots, and we can see some of the other things I'm about to show you. And I have no idea of time, so you're just going to have to bear with it. You can walk out, but Now, I wanted to, so this is making me even later, but I wanted to give a little digression. Because what I've been doing so far is talking about the sun as a machine for converting energy from nuclear fusion energy, potential energy, into kinetic energy, into convective energy, radiative energy. But you can't take an object that big that's lived for 4.5 billion years and expect to observe it for 10 years and know anything about it. But we have this is where sunspots come in. We've had a really good tracer. We have sunspot records that go all the way back to some Chinese observations a few thousand BC. We don't have any systematic observations until we started turning telescopes to the sun in 1610. And Galileo gets credit for discovering sunspots. He did not. But what he did do was the first to categorize them, study them, and actually identify that they were a solar phenomenon. People used to think they were up in the clouds, just blocking your view of the sun. And so since that time, we've been able to watch the sunspots systematically. And if you do that, an interesting thing appears. I said there was no clock on the sun. I was lying. There's no clock with a little dial on. But look at this. If all you do is look up on a given day, and remember Galileo went blind, so I'm not encouraging you to do this. If you just count, how many sunspots do I see on Monday? Put them down in your book. Your Excel spreadsheet, you would do it now. They didn't have that in the day. Next day, how many sunspots? Next day, and so on. And if you do that for 400 years, you have the record that we have now. And look what happens. Boom, 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 boom. The sun's beating. When there's lots of sunspots, we call it solar maximum. When there's not very many sunspots, we call it solar minimum. And you see it's a repeatable pattern. Now, it's repeatable in time, because notice that they're not all the same size, they're not all the same shapes. But there's and there's a little bit of variation in the time. But typically, the average is 11 years between maxima or between minima. So the sun has a regular 11-year cycle. And remember that sunspots are a magnetic field. So what's happening is, and you probably heard about this at the Earth too, is, and I'll show you this in a second, this is just counting sunspots, but the field that's related with it is enhancing, contracting, and it's also flipping. The north and south pole of the magnetic poles of the sun flips every 11 years. In the Earth, it's like every 30,000 years or 10,000 years, I can't remember the number. Sorry, it takes about 10 or 20,000 years, but it's every 700,000 years. On the sun, it takes a couple of years, and it does it every 11 years, which is actually quite remarkable when you consider how big the sun is, that it can do this regularly. So we watch all this, so that's a pattern in time. So if you're looking at a machine, if you're trying to reverse engineer a machine, you don't just look at it and go, oh yeah, it does this and it can make you coffee in the morning. You watch it and you look for patterns. You know, if it's a coffee machine and it makes a bleep at 7 a.m., you know that you start to get the idea that somebody likes to have their coffee started at 7 a.m. because they're going to get up at 7:15. And you can use these patterns to learn something about the machine that's making these patterns. So here we have a time pattern for the sun. And we can relate that to the structure of the atmosphere of the sun. And so here again is just a snapshot. This is 5 decades, 5 cycles, 1950, 60, 70. These are years. And here's the sunspot number. And the yellow curve is just the average through that number. Each of the blue dots here, 1, 2, 3, 4, 5, are taken from the ground of essentially their eclipse pictures. The moon blocks the sun, the corona shows up. And it's called the corona because it looks like a crown. And what's interesting is that if you take a look at the corona near solar maximum, so number 2 here, this is near solar minimum, so 1 and 2 here, you see a very complicated structure. This is the magnetic structure. I won't tell you the process. This is reflected sunlight off of electrons in the atmosphere, blah, 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 but it's structured by the magnetic field. So when the sun is very active and you have lots of sunspots, it's not just localized magnetic field. This magnetic field is spreading through the whole, not only the solar atmosphere, but all the way to the Earth. And so we see a complicated structure when there's lots of sunspots. And when you get to very few sunspots in solar minimum, it starts to look very simple. It actually starts to look like a regular bar magnet north and south. It's a little bit complicated because these little spikes, and that's because there's a solar wind that stretches the field out. But this is very simple structure, very complicated structure. So now we've got a relationship going all the way back to the core, to the actual structure, large-scale structure going through millions, hundreds of millions of kilometers outside the sun. If you look a little bit up here, now this is the instrument that brought me to the United States, although it's a Japanese instrument called Yoko. We were the guys who built this soft X-ray telescope. We're looking at X-rays emitted by the sun in the solar atmosphere. The temperatures are up here are somewhere between 2 and 5 million degrees. And so they're hot enough that they produce X-rays. And here we have a series of observations going from solar maximum to solar minimum. And look what happens. Lots of X-rays, lots of hot stuff, less and less and less, and then the whole sun effectively switches off in X-rays. It's still producing UV invisible, but it's switched off in the X-rays. And so that tells us another pattern. Not only is, remember the sunspots are also the magnetic field, that magnetic field defines this large-scale structure, and it also defines how much energy is available to heat the atmosphere. We don't understand why the sun's atmosphere is the temperature it is, because it doesn't make sense. It's a bit like running cold water into a bath and keeping one end warm, because it goes against the second law of thermodynamics. But the key is the magnetic field. And that's where the elastic band comes in. I'll use it more than once. So that's a little bit of physics of energy, right? This elastic band has very little energy. I mean, it has gravitational potential energy for the pedants amongst you. If I took my hand away, it would fall. But it's got very little other extra energy stored. It's in its minimum energy state. What happens if I stretch it? I've added energy to it. which is potential energy, kinetic energy, a little bit of heat and sound when it hits the wall, and then I've lost my key instrument. So what's happening is this magnetic field is storing energy that then some magical way, which we're not fully sure of, gets dissipated and produces all this heat. I'll come back to the elastic band in a second. So the magnetic field now is the whole story. It's based on the structure, it's based on the motions, it's based on the characteristics of the interior of the sun. It makes its way through to the surface, and then it defines everything above the surface. How hot it is, how that heat is distributed, what the structure of that atmosphere looks like. And that's, for the next 5 or 10 minutes, is the rest of my story, and it gets a little bit more active. The other pattern we have, I should point out, so here's another picture. Here's your 11-year beat. But now we're not looking at a little white dot. We're actually looking at this giant star. So we can actually look at where the sunspots are on the sun, not just that there's a sunspot. So when we look at where they are, we find a really interesting pattern. Near the beginning of a solar cycle, near the beginning of the rise, the sunspots appear at higher latitudes. As that cycle gets older, so halfway through or so, or 6 or 7 years through that 11-year cycle, they come nearer the equator. And so when you put all that together, you get this beautiful picture that we call the butterfly diagram, a series of butterfly wings. So now we have a spatial pattern. Now we're starting to look at that clockwork of the sun as a machine. We know its time pattern, so we know that the day, we know that it's turning around every 11 years, and we know that there's a spatial pattern of these sunspots, and that tells us an awful lot about what the sun looks like inside. Now this is going to be a very, very complicated movie, but it puts all of that stuff together. So, but now instead of looking at sunspots, we're even clever enough, and again I emphasize not me, other people, are clever enough that we can measure magnetic fields on the surface of the sun. We can use Zeeman splitting and some polarimetry stuff. And so what you're looking at here, instead of the light or the lack of light in a sunspot, you're looking at the magnetic field. So here is a sunspot pair, negative and positive polarity. Here is a sunspot group and pair. Notice there's another pattern. On the top, it's blue on the left and yellow on the right. On the bottom, it's yellow on the left and blue on the right. So now there's a pattern in the polarity. And we have a spatial pattern and we have a time pattern. And what's interesting is there's also an angle, I don't know if this shows it so well, but the sun rotates out of the board and into the board. So we call this the leading sunspot because it's ahead in terms of rotation direction. It's pointing towards the equator in both hemispheres. Blue slightly closer to the equator, yellow slightly closer to. So you have this red, blue, yellow pattern, yellow, blue pattern. They're pointed at the equator, and they're at different latitudes, and they have this time beat. All of that together allows us to work out this, what we call the dynamo process, the machine that produces the magnetic field. So I'm going to show you a movie, and I'm not going to show you it more than once, and it's very complicated. What you're going to see is, I think, 4 solar cycles in the magnetic field. What's going to happen, remember I told you the sun's field flips every 11 years? So if you look carefully here, it's mostly yellow at the top and mostly blue at the bottom. So that's your bar magnet north and south. You'll see that that flips. If you just look at the poles and nothing else, you'll see that that flips every solar cycle. But why does it flip? And it turns out, if you notice, that's yellow and blue is slightly northward, and this is blue and yellow is slightly southward. Those opposite polarities will drift in time, interact with what's at the poles, and eventually convert them to the other polarity. And that is the sun's machine for sloshing this field around. There's also, you'll see, so you've changed the sign. So you've gone from north and south to south-north. So the arrow on the magnetic field on that little diagram I showed flips, which means that you end up flipping north and south. So blue and yellow will become yellow and blue in the south. And then it will flip back, and then it will flip back again. So this is that whole solar cycle in a nutshell. So what it'll do is it'll stretch it out, so it'll show you how that works. So remember, each one of these pairs is a sunspot group. If we take it and make a projection of it so that it stretches in a flat plane here, and then we turn on the movie, and it goes really fast, and here's the time. There's the blue the blue drifting up. Here's solar minimum, hardly any sunspots. Now it's yellow-blue, blue-yellow. Here's these drifting poles. You get blue here. It'll turn to yellow in a minute. And I have to talk really fast. Right? And so you get all of these patterns, and you can actually see the equatorial things, and so on. This is amazing. I mean, we can take something as complicated as a star that was forged in, if you listen to the astronomers who don't really care about the sun, there's all these magic things happening very, very far away, and we're brilliant because we understand them. You don't understand them unless you... I don't have a board here, but what I do with my class is I say, here's an astrophysicist. You draw an axis, X and Y, and you put a point on it, which is their observations. And then you ask them to explain the observations, and you can draw a line through it, a line that way, a squiggle through it that goes through it. Any theory you work happens when you don't have any data. So you can be brilliant. Colliding black holes, exploding neutron stars, weird aliens with ray guns, whatever. They will all fit your data. We can't do that in the sun because we've got too much data. So I argue that we have to be more clever. But they would disagree with that. But it's really a very interesting, if you're an astronomer, this is your garden. This is where you play. There's so much data. There's so much ways to test your ideas that it really is an exciting field. It's just absolutely fantastic what's happening. And then admittedly, to be fair to my astronomy colleagues, it's easy to get lots of data when the star's really close. Right. So, okay. Now, just to put that stuff together, and here's what we can study now. We can actually see sunspots before they emerge because of this earthquake analogy. So here's what happens. The sunspot emerges. Here's the sunspot emerging. Now what's going to fade into simultaneously, this is observations, this is now the atmosphere above those sunspots. So here's the link. So far I've talked a little bit about the structure outside, but when these sunspots appear, they're appearing with magnetic field, and then that magnetic field is a new set of magnetic field is permeating that atmosphere. Let me show that again. So here's the sunspot emerging. That's a helioseismology observation, very tricky. Pops up, you start to see new dark features up there. There's your sunspot coming out. It's more complicated than just a nice little circle. It's tapping into that atmosphere, and you get these structures we call magnetic loops. And you can see already, that's your dynamic sun right there. So now I hope what I've done is start to make the connections from way back in the core to the magnetic field to now determining what's happening in that atmosphere. And that's where the cool stuff starts. Little physics lesson. I talked about bar magnets. Just to orient you, if you've ever done this experiment, you put the bar magnet down, you put a plastic cover over it, and you sprinkle iron filings. Anybody ever done that? Okay. And what happens is you get this pattern, right? It looks like this. There's your iron filings, and you can see the magnet. And you can see one's one pole and one's the other, and you get these nice field lines going between them. So if you take a cartoon version of that, and you just say, well, here's a bar magnet, here's the magnetic field lines, and here's something that is orange, so it must be the sun. But you can't see through the sun, so you cover the sun in, and you don't see the magnet anymore. All you have is a structure. And then if you happen to fill that structure with plasma, hot gas that's emitting radiation that we can actually see, you'd get something like this in terms of your cartoon. And here's the observations. Very, very similar. There's some really interesting differences, and again, that's another story. But what you see is very clearly, we cannot measure the magnetic, we can measure it on the surface, we can't measure it in the atmosphere, but we can work out its structure by looking at these emissions. And it's not that simple because it turns out this is what's known as an optically thin gas, which means your head is, all of your heads, not just, I'm not looking at one person in particular, is optically thick. In other words, I can't see the back of your head through your nose. But if you were made of sun material, I would be able to, and I wouldn't know if you were facing me or facing away. So it makes it difficult to pick out whether this is one big structure here or lots of structures going in lots of different directions, because everything adds up. But that's just to show you that we have to actually work hard. It's not all this easy. So, where's the dynamism come in? So this is a movie of that solar corona taken at about 1.5 million degrees. So we actually tailor our telescopes to only select specific wavelengths and therefore specific key temperatures. So this is about 1.5 million degrees. And notice, and here's the size of the Earth to scale. Here's the edge of the sun. There's lots of really interesting dark things going on. I'm going to show you some really cool ones of that in a second. And then you see that this is over the period of maybe an hour or 2 hours. And you're seeing it doesn't just sit still, right? It's not just a big yellow globe with a smiley face on it. The sun has all this extra stuff going on. All of that stuff that you're seeing, the changing size, the changing brightness, all has root cause in energy being sucked out of that magnetic field. Small amounts of energy compared to the size of the sun, but enough. And of course, we're selectively targeting. If you were to compare this in brightness to the equivalent brightness of the sun, it would be minuscule. But because we're targeting that temperature, the sun itself is we don't really see. We're only seeing stuff here because there's hot stuff up above the surface of the sun, and there's dark stuff blocking the hot stuff from our view. We don't actually see the emissions from the surface at this temperature. So these little faint things, is a bit like an eclipse, pop out and we get to see them. And you can see that they're changing in scale from about 100 to 150,000 kilometers, 300,000 or 400,000 kilometers. They're bouncing around a lot and everything's going on. And again, what's happening, here's my little elastic band. So if you think of the magnetic field as a rubber band, then remember it's rooted in those sunspots, which are rooted in the surface of the sun. And I showed you all that granulation stuff that's going on. So the whole surface that this field is rooted in is moving around all over the place. And what does that do? It stretches the magnetic field. And if you stretch a magnetic field, it's no longer in its Rebecca volunteered, although she didn't know. It's no longer in its lowest energy state, and it has stored energy. The trick that the sun does is tap into that stored energy and does stuff with it. That analogy is a bit closer to something I'm about to show you, but what it's doing here is releasing that energy in the form of heat. And it's making that atmosphere 1 million, 2 million, 3 million degrees. Now, what it also does is, that's a kind of continual, slow process. What it also does is more akin to what I just did. And that is, you take a long time to store up the energy. You put energy into the magnetic field, and then something catastrophic happens, and in this case, I let it go. And you release all of that energy. Where did it come down? Did I lose it? Oh, I did get Rebecca after all. Sorry, Rebecca, I didn't mean that. I'm not that good. And so what it does is it releases it. Somehow what's happening is the magnetic field gets so much energy pumped into it that it can't handle it. And a real analogy would be the elastic band would snap. And I don't think I've got the strength to do it. But if I pulled this and pulled it and pulled it and pulled it, I would make it snap, and there would be a release of energy. I'd get a sore finger and all those things. And that's what happens when you get things called solar flares. It's still magnetic field, but it's a dramatic release of all of that energy. So to orient you here, because there's a lot going on here, and I could talk for an hour on this one movie, and I'm not going to. This is your edge again. There's a sunspot in here. There's a little filament here. I'll talk about those in a second. And there's some magnetic structures. But notice it's fairly weak, fairly faint. There's not a lot of really hot material. Again, we're looking at 1 million, 1.5 million degrees. Here's what happens when the magnetic field snaps. Notice where it was empty is now full of stuff. And we have enough information that we know that this material, where it's fuzzy, is 20 million degrees Kelvin. I guess it doesn't like to be paused for too long. What you'll see also is these structures. Now remember, we're selecting a specific temperature. So if it goes too hot, we don't see it. And if it goes too cold, we don't see it. So you'll see this, it's called an arcade. Big elongated structure with these magnetic fields going from one side to the other. And then you'll see them heating and then cooling. See how they go dark? Look at what happens when they're interacting with the surface. You have these two rivers of interaction that move apart as these structures get bigger, their foot points move apart. It's a bigger and bigger arch. And if you're looking really closely, you'll see these things we call tadpoles. No idea what those are. We sort of have some ideas. But when you actually look at them with a spectrometer and so on, they have absolutely no material inside them. It's not that they're too hot or too cold to be seen. They actually have no material in them. And so there's some interesting theories about what those are. But notice that this empty corona, and then again the Earth is maybe the size of one of those O's, maybe a little bit bigger. But look at this thing. Right? So you have this big arcade of material. So that's one movie of a solar flare. And again, it's release of magnetic energy. I'm not responsible for the music on this particular thing. NASA is. If it gets annoying, I'll switch the sound off, but I need the sound later. What this is now a more recent observation from the Solar Dynamics Observatory. It's just beautiful. It's not as exciting in terms of big eruptions and stuff. I'll show you those in a second. But here is, again, a relatively empty corona with a structure in it. And this structure you can see now, hopefully you can see the magnetic field structure. And this is a localized release of energy in a solar flare. And again, NASA is responsible for the music. This is as close as the sun comes to being a fiery ball. The sound effects are good, but the music really is. So, building up the story. We've now created all this magnetic field and we've released it and we've produced a flare. But it turns out it's a little bit more complicated than that because we're still focused on relatively close to the sun. Here's another fiery ball picture. And what this is now is we're looking at ultraviolet light. The temperatures here are more like 10,000, 20,000, 40,000 degrees, a little bit cooler, a little bit lower in the atmosphere. But what I like about this is the whole sun. This is actually an emission line of helium, singly ionized helium, if you're interested. But what I want to draw your attention to is these dark ribbons. And these are called solar filaments. I'm going to show you a solar prominence, which most of you have maybe heard of, and maybe you haven't heard of filaments. They're the same thing. They were just given different names because they were observed at a time when we didn't know they were the same thing. But I'll show you the prominences in a second. So here is a very active phase. There's a couple of sunspots where you see this plage and this extra bright stuff. Did anybody do the Chronicle crossword? There was a solar clue in it this morning, but it was wrong. It said, I think it was this morning, maybe yesterday, it says, what is the bright region around a sunspot called? And they called it a solar flare. It's not, it's called faculae or plage. A solar flare is a dynamic. But anyway. So you have, I'm sure they got it from the LA Times. So you have these filaments, and they're all over the place. Some are very long. These are called polar filaments. You'll get some in little ones like this one, near active regions, near sunspots. So just watch this movie. It's not quite as dramatic, but it's what you'll see. Watch those filaments, because now what we're doing, we're making our first steps in this story to leaving the sun. And what's in the path of stuff that leaves the sun? Us, right? So this is the first step towards that in the last few slides that I'm about to show. So the sun's rotating. Now it's a little bit more casual speed. Boom. See that? Look how big it was. Here's another one that goes off there. There's still active stuff going on. There's another one going off there. Typically, during solar maximum, you get 2 or 3 of these big eruptions a day. During solar minimum, you might get 1 every 2 or 3 days. But this is the dynamic sun. I could speed it up and make it look more dynamic, but these things are immense. And what's difficult here, from the physics point of view, the reason these things are dark is because it's like a slinky, one way of thinking about it. So imagine a magnetic field that's been coiled up into a kind of spring shape or a slinky. Well, what happens is it sits above the surface, and it's all twisted. Gravity's pulling all the material down to the surface. But if you have a magnetic field, and because these are charged particles, what happens is they stick to the magnetic field. Stick is not the technical term, but it'll work. So they stick to the magnetic field, and they get held up in the atmosphere, inside the bottom part of this slinky. What's interesting is that it's cool chromospheric material, so it's 40,000 degrees, being held up in an atmosphere that's 1 million or 2 million degrees. So what does that do? It shows up as dark. It's absorbing the stuff from below, and it shows up as dark, and so we see it in contrast against that background. The problem is, in terms of the physics, what you have to do is to explain this, you have to have a way of, we can understand how you slowly increase the energy. So you slowly over days increase the energy, and all of a sudden you release it in a matter of minutes or hours. That's very difficult to do in terms of, say, if you were coming up with a model, because one process is slow and steady, and the other one is a sudden catastrophic change. And if you program it to be catastrophic, you never get the slow steady part. And if you program it to be slow steady, it's very hard to get it to be catastrophic. So there's a lot of challenges in terms of trying to understand the physics of these things, but that's what we're here for, is the challenges. If we look a little bit closer now, this is where it starts to get really interesting. You recognize this now. It's the chromosphere of the sun, 40,000 degrees. You don't see much off to the left there, but here's what one of these things look like close up. Boom. They're not only beautiful, but they're very dramatic. They come from next to nothing, and suddenly they're doing this. And then this is about, let's see, maybe a little bit bigger than the hand is the size of the Earth. Very, very large structures. And it gets better. I think that's this. Oh, this is a different one. Looks the same because it's the same wavelength, the same part of the sun. So not only do we have a hard time keeping them building up energy and then suddenly release, but no one is the same as any other. So that becomes very, very difficult to explain them all. It's a bit like saying everybody in Houston are Texans and they all behave the same and act the same and talk the same, which is very clearly not true. So it gets very hard to explain that mix. Now, this is one of my favorites. There's a little feature on there that looks like somehow I've scratched the lens. See this tiny little thing? Ah! I hate Macs for the iPad. Okay, let me pretend you didn't see that. See this little tiny thing in there? It's a filament above a sunspot. It's about 5,000 kilometers above the surface, and it's about 10, 20,000 kilometers long. Tiny compared to the size of the sun, and you've already seen what happens. But this is what happens. It's been sitting there for a little while, building up energy, and for some reason, boom, huge. Fills that large volume. You can actually see some splashback on the sun where it hits back. So the material is being expulsed. Gravity always wins, so some of it gets pulled back. You can see that it gets heated because it shows up as bright, and then it cools and shows up as dark again. And so how do you explain that? Right? But it's just beautiful anyway, so that's what I like to, so that's what I wanted to show you there. Now, we're getting further and further, we're almost at the end. We're getting further and further away from the sun now. So I have to explain this a little bit. This is an amalgam of 3 different observations. Because in order to see the faint stuff out in the corona, we have to block the sun, right? So we create fake eclipses. And there's 2 fake eclipses here from 2 different telescopes. And then there's a third telescope that's producing what's inside, actually producing the sun. And the sun really isn't green, although that's actually in some senses it is green, but that's another story. Because this is ultraviolet light, there's no color, doesn't matter, right? It's not red, it's not yellow, it's just ultraviolet. So for us to distinguish which telescope we're looking at, we pick a color. So this is 195 angstroms, which is, again, I think that's the 1.5 million. The other one was 1 million. So this is 1.5 million degrees. And so what we've done is, this big circle is the big eclipse, so we've blocked the sun so that we can see all of this faint stuff out here. This circle is the second eclipse from a different telescope, so we've blocked closer to the sun. We're still blocking the whole sun, but a little bit closer. So that allows us to see the stuff in this region here. And then we've taken that region where we had the plates that blocked the sun and stuck in the ultraviolet image of the sun. And these are all synchronized both in space, so they're all oriented properly, and in time. So now we can see, what does the sun do over, so remember, this is 1.5 million kilometers. This is about 2.5 solar radii, so that's about 4 million kilometers across, and then this goes all the way out to, I think, 30 solar radii, or 40 million across, million kilometers. Still a long way away from the Earth. Watch what happens now. And the Earth is where you are. So the Earth is out there. This is another great movie. Boom. That little thing that we saw that sort of ran into the edges because we didn't have a big field of view, when we increased the field of view, this is what happens. So you can see there's a little filament in there, and all of a sudden, this is bigger than the sun itself. Now, it looks really dense. It looks like a big blob, but it's still more diffused in an industrial vacuum. There's very little particles in here. But what it's doing is reflecting the light from the surface of the sun off of these electrons and directing them towards your eye at the Earth. And so suddenly, this tiny little thing has disrupted the whole structure of the solar corona. Now, the nice thing about this one is you're the Earth. So this one is not coming near you. It's going over there. So most of these events are not directed towards the Earth. What happens when they're directed towards the Earth? We call them halo CMEs. And again, this gets a little bit, a small complication. Because we've blocked out the sun, you can't see anything coming right along that line because you've stuck your hand. If you stick your hand up, and I walk towards you and stay behind your hand, you don't see me coming until I slap you in the back of the head. So what we've done here, the white circle is where the sun is, the red circle is the disk, and we've blocked the sun. So when this structure comes out, remember it gets really big, we only start to see it when it gets beyond the circle. We call it a halo because it ends up being a complete halo around the disk that we've put in there. And now it's heading towards the Earth. And so you'll see a couple of interesting things. You'll see the structure, and you'll see something else. Right, a bunch of activity, boom. You notice there's something else? Anybody want to tell me what the something else is? Interference. The snow, yeah. So what's happening now, so this is another observation. This telescope is 1 million miles away from the Earth, towards the sun. It's blocking the sun so it doesn't see that, we call this, and again, remember I said we're good at names, a spot on the sun, it's called a sunspot. This is called a coronal mass ejection. It's the ejection of mass from the corona. And it's coming right at you. And so you see this halo, you see some structure, it's not completely uniform. As soon as so we've got this camera sitting looking at this thing, the doors are open, the exposure's running, and it's a CCD camera, like you're on your phone. It's a digital camera. It costs $1 million, but it's a digital camera. And suddenly, it's not just the light that's getting there, there's all of this stuff. And each one of those dots, see if I can pause it. Yeah, missed. That won't stop for me. Each one of those dots is a high energy proton, maybe an alpha particle, a high energy proton hitting that camera. And so all of a sudden, the particle flux, this is the radiation. I was talking to Scott earlier. This is the radiation that astronauts worry about, that fries satellites, that does all this stuff at the Earth that we're worried about. And what's happening is, I'm trying to wonder whether I want to go into this physics. What's happening is this big ejection of mass. So there's a thing called the solar wind. If you look at these, see how there's all these striations? So there's a constant outflow of stuff from the sun. And it's traveling in the ecliptic plane, it's traveling about 400 kilometers a second, which is pretty fast. These coronal mass ejections can move up to several million miles an hour, or 2 to 5,000 kilometers per second. So if you think of the solar wind as a flowing river, suddenly you've got this speedboat plowing through it. And what that does is it creates a shock. And it creates a wake, but it creates a shock. And those shocks turns out to be really good at taking particles and speeding them up. And so that shock takes the ambient protons and electrons and so on and accelerates them up close to the speed of light. And it's very hard to get anything near the speed of light when it has any kind of mass. And the protons are pretty heavy in the scheme of things. So what's happening is that this magnetic, fast-moving object is interacting on its way to the Earth and producing a bunch of dangerous radiation that then interacts with anything that's in space, including the Earth. We're lucky that we have a magnetic field, and so we're protected from that radiation. But if you're a telecommunications satellite, my favorite story, I'll tell one story. there's a big event in 1989. I'll tell two stories. Big event in 1989. And what this does is it energizes the whole magnetic system of the Earth, which includes the ionosphere. And so the ionosphere became more charged and it started emitting more radio radiation, radio waves. In California, in Los Angeles, a whole bunch of garage doors started opening and closing for no reason. Because in the old days, it used to be radio signatures, radio receivers, not infrared. Because it was California, nobody noticed anything different, and it was okay. But it has this effect. And it was but the key thing to think about where Los Angeles is. It's not in the North Pole. It's not where the northern lights are or the southern lights are. It's actually at relatively low latitudes. 2003, if you had left Houston, west or east, just get away from the city lights, in March, I think it was, no, November, October, November, you would have seen aurora outside of Houston, red aurora. These storms can get so big that they compress the Earth's magnetic field and you get this particle injections that produce all these nice colorful lights as far south as 30 degrees north, which is where we are. Big impact on the Earth's magnetic environment. And nowadays we're so reliant. How many of you use GPS to get here? Okay? We are so reliant on space technology now that this is a problem. 150 years ago, there was a giant storm, and the telegraph cables between Maine and Boston, they could switch the batteries off, and there was enough power being put into the system from the sun that they could actually work the telegraph with no batteries. And that was kind of amazing. But that was the limit of our technology then. Now you can't do anything. None of you can do anything, including myself, without your phone. And your phone is all dependent on that satellite up there doing what you need it to do, talking to whoever you need to do. And those satellites are up in space when the sun does this. So it's very interesting. Luckily, it doesn't do it all the time. It doesn't always hit the Earth, and it's not always as strong as some of the ones that we're showing. I'm almost finished. Here's just another version of that same thing. You'll see this is a different storm. Here's the sun, here's the eclipse. This is a computational artifact. We have to hold the disk with something, so it's a little bit like a dentist mirror. So sometimes we can't completely remove the bar, and so it shows up. But again, here's this big picture. You're the Earth. The storm's coming towards you. There's a nice, beautiful storm. And then a few minutes later, boom. Very, very high increase in the particle flux. So, big giant cloud, collapses and spins, creates heat and temperature in higher densities, allows protons to come together to create, or to release energy, to distribute that energy through the interior of a star, sets up an internal structure both in temperature and density. It's already moving, conservation of angular momentum, that star collapsing is moving. The temperature structure creates other kinds of motion, differential rotation, rigid rotation in the interior, convective motions in the exterior. That serves to create a magnetic field. The magnetic field builds up, becomes like a hot air balloon, works its way to the surface, shows up as a sunspot, does some really cool things with the corona, winds up the magnetic field, releases that magnetic field and produces nice pretty flares with bad music, erupts even further and works its way towards the Earth where it does this. And we now have the capability with the technology we have and the satellites we've built to follow these things all the way from the sun on the right. Here you see it moving out. We can actually observe it all the way from sun to mud, we call it. There's other models where we can look at how the ionosphere is affected and so on. So we can start to look at this big picture. We call this space weather, but that's another story. So we can actually start to look at the sun and how it affects the Earth. And remember, the sun's a star, so I haven't even told the story of how we use the sun to understand stars. Just how it's interacting with the Earth. So what happens at the Earth? Well, that's another story. All right. Thank you. Anybody want to tell me the two pieces of music and not David or Zoe? Mahler 5 and Czech 4. All right, so there's a question. Was that a question at the back and then one over here? Yes, sir.
The question is the sun getting cooler, or is the energy preserved in a way?
So the temperature structure, while it's on the main sequence, is fairly stable. The activity can change, and that's an interesting question. The sun over time is getting brighter because it's producing, there's a bigger core now producing more hydrogen. When it gets to the end of its main sequence life, which is another 4.5 billion years from now, so set your alarm, it will run out of hydrogen in the core. And so what will happen is it won't be generating that pressure that holds up the core against gravity, and so it will collapse a little bit more. When it collapses, it gets hotter, and it starts to get hot enough to transform helium into carbon. As a result of that collapse in the core, you have to conserve momentum, so the outer envelope expands, and the sun will become a red giant star, and it will completely engulf the orbit of Venus and get pretty close to the orbit of the Earth. And so then it will be a cooler star on average, but it'll be a brighter star because it'll be much bigger. And then there's a bunch of other stuff that goes on after that. When it starts running out of helium, it starts to convert carbon to nitrogen, nitrogen to oxygen, and all the way up the chain. And eventually it'll turn into, I guess, a red dwarf star. And it'll collapse down and form a little red dwarf core. So the temperature structure is sort of, will do that kind of pattern. The activity structure is rather interesting because it's, while I talked about this nice 11-year beat, you may have seen in the news a few years ago that the sun kind of went quiet for a little bit longer than we were hoping for, and that this current sunspot maximum is very short. That's a real concern because what I didn't show in the plot is between the years 1645 and the year 1715, there was hardly any sunspots on the sun, even though we were looking. It wasn't because Galileo started in 1610. Even though we were looking, there was no sunspot. That machine switched off. And we had stronger winters. The Hudson was frozen, the Thames were frozen. There was ice fares as late as March in places that never had them in March. So there's a real climatic effect on the climate when the sunspots are switched off for effectively 7 cycles. So when the sun went quiet recently, there was a lot of discussion about whether we were entering another minimum period like that. Now we've come out of it, but we haven't come out of it very strongly. And so there's still some question as how what's going to happen as we go. So there's a different argument in terms of the sun's behavior and in terms of its activity, whether you call that temperature or magnetic activity. It's an interesting question. Scott, you had that.
Does the same science, or is there enough science to determine if the same mechanisms that drive our sun drive larger stars and smaller stars?
So that's a really good question. From the perspective that I've been giving on the magnetic field, let me back up a little bit. Most of what up until 20 years or 30 years ago, what we knew about the interior of the sun came from modeling the sun. So we had these models that said, if you have this much mass and you stick it under gravity, and we understand that there's a pressure created when you heat stuff, and you put all that together, you actually get a really good picture of the sun. And you could argue, well, the model's not all that good. But it turns out that the reaction rate in the core is so sensitive to temperature. It's temperature, and some reactions are temperature to the power 16, right? So you change the temperature by a factor of 2. Anybody can do 2 to the power 16, David? 2 to the power 16 is what, right? It's 1,000, 30,000. It's about 100,000 times. The reaction rate would increase by 100,000 times. Because of that sensitivity, you can't change the parameters very much. So that means the model ended up being really, really good. It predicted the model of the interior of the sun. Then we started to be able to probe the interior sun, and it turns out that model, apart from a few glitches in here and there, was really, really good. What that tells you is we can actually do pretty well at modeling the structure of a star, and you can then apply that to other stars. And so far, that's worked out really well. There is now an effort to do what's called asteroseismology, where we have enough data from some stars that we can look at how they're oscillating and start to probe their interiors the way we can do it with the sun. And the reason that's important is the crux of your question. We have this process that works for the sun. We call it the solar dynamo. Move charges around in a conducting medium and produce magnetic field. Everything seems to work, and we have this really good model. One star. We don't know if we took that model and applied it to another star, if it would do what it would produce a star that does what that star does. And we can't do that because we don't know the astroseismology of these stars. So what we have to do is build up that data. And we may find that the same when we find these other planetary systems. So the analogy to the planetary systems is we now have many more systems. But almost all of the systems that we've seen have big giant Jupiters around about the Earth's distance from the star, or even closer in. That makes no sense compared to the model that we have for our solar system. Now you can do two things. You can say, I'm an idiot, I'm completely wrong, and our solar system is rather unique. Or you can blame the data. So we blame the data. We have a selection effect, right? If you had a 6-foot wall and you had everybody walk behind it, I can't remember, I don't think I've seen you standing up, but I may just see the top of your head, but you'd certainly see me. And so you would start to see people who were above that height of that wall, and you'd go, wow, everybody behind the fences, but you're not seeing the people who are hidden. So now we're getting more data, we're starting to see more systems. It's the same with stars. We only have one dynamo process that we can see working, and we can measure, and we can test, and we can do all that stuff. Until we get that kind of data for other stars, we don't know. So that's a long way of saying I don't know to your question. But because of the sensitivity to this nuclear fusion, which we believe powers almost all stars, neutron stars and black holes are doing other things. But when you look at those processes, we think we have a really good understanding, and so that that's why we can talk about stars being similar types. The spectral type, Cepheid variables, or variables that are used as standard candles because we're assumed to be the same brightness. All those different things. It's very, very sophisticated, but I think very well understood. We can always be proven wrong, and it takes data to do that, and that's what we're working with. With the James Webb Space Telescope coming up, that may do change a whole bunch of viewpoints on that. Sir?
I've been a proud member of the Rice Space Institute for many years under Professor Wright, and I'd like to thank you for your leadership. It's a real
Oh, it's nice of you.
I have a couple of questions. One with respect to the gradual and then cataclysmic dynamism of some of the processes. With respect to the reverse of polarity, is there an equipose event or equipose time where there's a graduality and then all of a sudden a cataclysmic reverse?
So the question is about the process of the reversing, in case you didn't hear it, and whether it's related. Essentially, it's the same process every time, and that is that it's fairly cataclysmic when you think about the size of this object and it's being able to flip in 2 years. But that seems to be fairly regular. And it's governed by, what's really interesting is it's governed by an interesting, we call it the conveyor belt. There's an interesting flow underneath the surface that takes magnetic flux. I was talking about the stuff that comes out, but there's a flow of material back up to the poles underneath the surface, and that takes 22 years. And so if you think about the cycle for sunspots is every 11 years, the sunspots don't care if they're blue and yellow or yellow and blue. They don't really care. The activity that I've shown you doesn't matter. It just matters that there's complexity and there's motion. But if you look at the magnetic cycle, if you went from blue, yellow, yellow, blue, blue, yellow, that's 22 years. So the magnetic cycle is a 22-year cycle, which is a proper cycle, that really what we should be talking about. But because of all the manifestations that we see are these sunspots releasing this energy, we talk about it as an 11-year cycle. So that process is fairly, well, up until a few years ago, I would have said it's fairly routine. And the energy is constantly being produced, and then because of the nature of, you're turning poloidal field like this into field like that because of the rotation. If you convert all of it that way, you're dead, you're done, the sun's done. There's another process that converts it back, and I can't bend my arm, so it goes like this and like that. So there's a process that converts, then goes from, we call it poloidal, pole to pole. So there's a mechanism that the rotation takes this polar oriented field and makes it equatorially oriented, and that everything would stop there if there was no source to turn it back.
So my question is, right at that
Right.
equipoloidal period.
What-
Can
It's
you-
a- it's a- it-
is there a discernible, measurable event?
No. So what you see is the sunspots dying off, a lower level of activity. And think about it, and I can't make my arm do 360, but think about what I just did. I stopped, admittedly, but what's happening is this.
Okay.
And then it's coming back. So it's actually a continuous process. What's interesting, and it's not that your question isn't of relevance, actually, what's interesting is when that doesn't work. And so a few years ago, we were worried that that process had stopped. And when the Maunder minimum, that 70-year period where that wasn't working, again, think about a giant clockwork toy that's working away. It's easy to flick the spring and give it an extra little time. If it completely stops, it's very hard to get that big machine wound up again. And yet the sun did that. So there's some really interesting underlying physics that we don't understand is if you switch that machine off, what is it that starts it up again? It has to be to the same kind of physics. The sun hasn't decided to, you know what, I don't like Newtonian physics, I'm going to use something, right? So there's some really interesting questions at the root of some of the things you said, but from the basic process is smooth and continuous. It's not like this, this is a 2-year period, but it's 11 years that it sits up here for a while. And you saw that magnetic movie, although it was really fast, where there's this constant dispersal of the flux in the sunspots to the poles, and it's that process that flips everything over. There's a question here, and then back here, over here, and here.
Possible, has anybody modeled when you do have these unexpected lulls? I mean, it's, as you make the point, there's a huge amount of, for want of a better term, momentum involved in the cycle continuing smoothly. Could it be the case that for whatever reason you're having a period of chaos where things get perturbed and then eventually the forces align again?
Well, so the actual word I was going to use was chaos, and not in the sense of head for the hills, run away, but in the sense of the chaotic theory. If you remember all those Mandelbrot sets that everybody was buying the coffee table books about, there was an idea that, and chaos actually is a predictive tool, right? So you get all this fractal dimensions, and you get all these different things that come out, and you get these strange attractors and bifurcations. And so there is at least one theory I heard of that it could explain that because there was a chaotic component, that grew in strength and switched off the machine. But it still had its own behavior, and the cycle came back because then that part ceased to dominate. So the other thing was working out. That's the only one I know of that's talked about. Now, there's some other recent theories about now that we're understanding this subsurface flow, there's a lot of people looking at the physics of that and how it might switch off. And if they can work out how they can switch it. Now, the switching off is easy. You just let it die off. But in order to do that, they can maybe say, oh yeah, we can produce a minimum, but they have to answer the question is how you come back out of it. And there's a lot of work, actually, if you look at some of the work from the University of Colorado and up there, there's a lot of stuff coming out of there that's related to that. So I think there was one here, one there, one, well, 1, 2, 3. Yes, sir.
Yeah, a couple years ago, I guess, they were talking about how they were thinking Voyager has left the solar system, and one of the ways I imagine that they would detect that would be maybe a change in the magnetic, direction of whatever north is in the solar system, and when they left it, my understanding is they haven't detected such a thing, but they're using other means, like they think they detected radiation from outside the solar system, so they think it's left the solar system. My question is, if the poles flip every 22 years or whatever it is, that would be the ultimate proof, I would imagine. I'm asking this as a question, that if we detect the poles flip on the sun, and they have or have not out in Voyager, then that would be like definitive proof, wouldn't it?
Well, yeah, except for the complication, and it's a question we've even asked ourselves actually a while back. So much happens between when it leaves the sun and when it gets out there. There's a lot of turbulence, there's a lot of mixing of fields, and it actually gets very difficult to determine the absolute polarity and how long it takes to propagate. What we were worried about, and this sort of relates to the question, is if the sun is constantly sending out magnetic flux of whatever polarity, whatever sign, there's going to be a big buildup of magnetic flux in the solar system, and we don't observe that. So there's a process by which some flux gets cancelled and returned back to the sun, and some gets ejected out, and then that process mixes everything up. And so it keeps what's called the interplanetary magnetic field at a rough balance. Now, on the Voyager question, again, theorists can do anything. And so there was one theory that said we have transitioned from the magnetic environment of the sun to the magnetic environment interstellar space because we saw this transition. We've left the solar system. And everybody hailed that, and it was all great. Then some other theory came along and said, well, actually, because the theory was that the interstellar magnetic field was oriented differently from the solar field. Well, someone else came along and said, well, because of mixing and turbulence at the boundaries, the interstellar magnetic field could be oriented the same way as the solar magnetic field, and so you haven't crossed, or whatever it is. The way I like to think about Voyager, the analogy I would give for Voyager, and why I think it's how you define the solar system becomes an interesting issue, because the Oort cloud is still a long way away, right? But the analogy, and Texas is a good example for this, right? If you happen to be driving to Dallas from Houston, you're driving along, I guess it's 45 or 35, right? When do you know you're in Dallas? All this nice countryside, that's your environment for a long, once you've left Houston, all this nice quiet countryside. Some houses start to pick up. So there's a few houses, and you think, oh, I'm getting close to a city, I wonder if it's Dallas. Then the houses get even more dense. Well, I'm getting to a pretty big city, right? I wonder if it's Dallas. And then it gets really dense, and you're like, well, I wonder if it's only until you get to the center and you see the big sign that says you're in Dallas that you know you're in Dallas. So, but you do know that you're getting close because the density of the houses is increasing. So what Voyager saw was a bunch of particles. So all these particles are coming in from the interstellar medium into the heliosphere, the solar environment. They're in very small proportions. So you measure all your solar particles, and Voyager measures particles. You measure lots of solar particles, a little bit of interstellar particles. As you get close to the boundary, the numbers change, and if you cross the boundary, it looks like this, and that's what they saw. It doesn't mean they've reached the center of Dallas and they actually know they're in Dallas. So they don't know that they've really left the solar system. What they've done is seen the kind of housing. There's no longer farmhouses, it's townhouses. And they've seen that transition, so there's far more townhouses than farmhouses. And that's the argument they're using to say, we're in a different environment, we've left the solar system. It's always open to question, and then of course these boundaries aren't nice and spherical and thin, they're complicated structures. And
would a shift in the magnetic direction indicate if they do come across such a shift?
if it was nice and big and uniform, and I was trying to point out that it's not. So it's a bit like, it's just very chaotic, and so you're seeing fields in all sorts of directions, and so you pick the average, and if there was a large-scale average difference, you could argue that, and then someone would come along and say, no, you expect it to be the other way. So you just have to see. We just don't know enough of what's going on out there. That's why, for years, we've fought against them shutting off Voyager, because it's the only thing that's ever got out there, and it's taken 1977, it's taken, what, 47 years? Uh-oh.
There are refreshments out in the commons. They would be available.
Sorry.
Is that right?
Yeah, thanks.